All right, let's get into a discussion on concavity of functions. We're going to find this concavity by using derivatives. So first of all, what does it mean for a function to possess concavity? And that word concavity we've heard before when we discuss, things like polygons and maybe even mirrors in science class. But concavity basically means you're either concave up or you're concave down. And if you're concave up, that means that your general shape of your graph would kind of hold water. That's how I always thought of it. If you're concave down, that means that water would sort of always just kind of rush off of you. So if you're concave up, you're kind of shaped like like a bowl or something, and if you're concave down, you're shaped like a mountain. Sometimes they're not always so easy to see though. This is concave up, this is concave down, but it's barely that. Alright, and then in a function like this, where we have a cubic function over here, you can see that in this area right here, it would seem that it's concave up, and right here, it would seem that it's concave down, and it is. There's a point at which the concavity changes, which we'll get into a little bit in this video, but I'll dedicate another video to it specifically. That's called the inflection point. So we're going to use the second derivative to find all this stuff. Alright, so let's get into it. Find the first derivative. Negative 3x squared plus 8x. I'm using the power rule right there. If you're a little bit fuzzy on that, or if you have no idea how I got that, just go check that video out, either on my channel or somebody else. Derivatives are, the shortcuts especially are pretty easy to learn. There are a couple basic ones: the power rule, the product rule, the quotient rule, the chain rule. Very quickly though, what I'm doing there is I'm taking this number, multiplying it by this number, negative 3, or 3 times negative 1, and then just reducing the exponent by 1. 2 times 4 is 8, and then reducing that exponent by 1. 2 minus 1 is 1. Alright, so I've got my first derivative. I don't really care much about that. We use the first derivative in a couple of other videos when we're talking about increasing or decreasing function intervals. Alright, we're talking about minimums and maximums, right, those critical points. I'm not interested in that right now. What I'm interested in is our second derivative. So take the derivative of the first derivative and we get negative 6x plus 8. That's our second derivative. That determines concavity. Second derivative determines concavity. Solve this for set it equal to 0 and solve. So we get negative 6x is equal to negative 8. So we get 4 over 3, it would seem. 8 divided by 6 is 4 over 3. So that is the point where we're really interested in, 4 over 3. So 4 over 3 on our graph is, let me zoom in a little bit here. 4 over 3 is, this is an x value, so here's be 3 over 3. This would be 6 over 3. So 4 over 3 is like 4 over 3 is 1.33. So this is 1.5, this is 1.25. So it looks like it's going to be like somewhere in here. Alright, that's where x equals 4 over 3. Right there. Alright, maybe I'll put that point in red, because it's a really important point. That is called our inflection point. But for this video, let's not really worry too much about that particular point. Let's worry about how do we write these intervals of concavity. So what we want to do is do our second derivative test and relate that to our function. So in my past couple of videos, you've seen me use these number line tests. So I'm going to pick a number to the left of 4/3. Let's pick 0. That's the smartest number to pick. And we're going to test it inside our second derivative. So plug in 0 right here. Negative 6 times 0 obviously is 0, plus 8 is a positive number. That means our graph is concave up. When the second derivative is positive, the graph is concave up. So that would mean that it kind of holds water, right? Let's pick a number to the right of 4/3. How about 2? So let's plug in 2 into our second derivative. We get negative 12 plus 8. That's a negative 4. So that means the graph is concave down. That means it wouldn't hold water. It would kind of repel water. Where the graph changes from concave up to concave down is called the inflection point. That's called the inflection point. So the graph from negative infinity to here is concave up, and from there to positive infinity is concave down. So let's write that in a nice sort of interval notation. So concave up was from negative infinity to 4/3, and it switches concavity at 4/3, and it goes down, concave down from 4/3 to infinity forever. So there you go. Really quick little 6.5-minute video on concavity. Alright, I'm sure you'll probably find better diagrams out there to describe what concavity means in the first place, but again, I think about it as, you know, you either hold water or you don't hold water. If you hold water, you're concave up. If you can't hold water, you're concave down. Pretty easy, I think. And this is all about the second derivative. Alright, cool. Thanks for watching, and look forward to my next video, which will talk a little bit more about this inflection point, maybe give some more examples. So, thanks for watching.